So first, we're going to go over the basic system parameters that need to be considered when selecting a valve. Those include flow, pressure, temperature, media, viscosity, and environment. So flow occurs when a fluid or gas moves to an area of high pressure to low pressure. In a valve, flow is from the higher pressure inlet to the lower pressure outlet. The flow through a valve depends on a number of factors, including the diameter and shape of the flow path. The flow coefficient, which is provided by the valve manufacturer, can be used to help select the right valve for an application. The flow coefficient is represented in valve specs as C sub V, and a higher C sub V means a higher flow rate. Keep in mind that higher C sub V does not necessarily mean it's a better valve for your application. The C sub V is the number of US gallons per minute that will flow through a valve with a 1 psi pressure drop at 60 degrees Fahrenheit. So the flow coefficient of valve is a relative measure of its efficiency at allowing flow. For compressible fluids like gases, calculating C sub V is a little more complex, but it's still an effective way to size valves. Valve design factors that influence C sub V include the size and geometry of the flow path. For example, the larger the orifice, the greater the flow capacity. An example on this slide, both valves contain half-inch tube connections, but the ball valve on the left provides minimal resistance to flow. It has a C sub V of 7.5, while the needle valve on the right has a flow path that restricts the flow and has a C sub V of only 2.1. Swagelok publishes a valve sizing bulletin that you can find on swagelok.com, and it can help you pick the appropriate C sub V for your application. Next parameter in selecting a valve are pressure and temperature. And we put these two together because they affect each other. For pressure, you need to consider system maximum pressure, which is the maximum pressure the valve could see, and operating pressure, which is the normal operating condition. Like pressure limitations, every valve has a maximum minimum design temperature also. It shouldn't be exceeded. Temperature of your application will affect the allowable pressure. When temperature rises, the strength of materials decreases. With valves, that usually means that as the temperature rises, pressure rating goes down. The seal material is often the pressure temperature limiting component of the valve. The pressure differential is also important for flow. Delta P is the difference between the upstream and the downstream pressure across the valve. The pressure drop occurs when a fluid moves through a valve and is required to have flow. A valve with a globe pattern will have a higher pressure drop across the seat than a similar sized ball valve where the flow is straight through. With respect to valve selection, the higher the pressure differential, the more impact system pressure might have on wear of internal components. System media is another important consideration. Two primary forms of system media are gas and liquid. And media can be anything from inert gases like nitrogen or argon to corrosive media like hydrogen sulfide. When selecting a valve, you want to think about valve construction and how it relates to potential leakage. For instance, a metal-to-metal diaphragm seal may be more appropriate for corrosive gases than a soft-seated valve with a plastic or an elastomeric stem packing. Chemical compatibility is another important consideration. For example, embrittlement or stress corrosion cracking can occur if the wrong material is chosen for your media. There's a number of chemical compatibility charts available on the internet that can help you select chemically compatible components. Cole-Parmer and DuPont are two that I use often. The viscosity of your system media also affects flow coefficient. Tar pictured here is highly viscous, flows very slowly, and to achieve the same flow rate as a liquid with a low viscosity, like beer, you'd have to select a valve with a much higher C sub V. The last system parameter we're going to talk about is environment. It's important to consider the physical location of your valve. Will it be in a climate-controlled environment or outside exposed to the elements? The corrosiveness of the environment will also have a major impact on the material selected for the valve. For example, will it be in a saltwater environment like on an offshore oil rig? Vibration should also be considered. Will be close to a pump or compressor and exposed to high vibration.